Hello, this is Arjun Shukla from Team 12 for CS471, and I am just going to read our paper that we wrote for the Syngenta crop competition. It's called Lost in the Maze, Predicting Corn Yields Using Collaborative Filtering Neural Networks with Embedding Layers and Random Forest Models. Introduction. Syngenta Corporation is a global company that is focused on sustainably feeding the ever-growing human population. In their mission for food security, they have been branching out to the masses in order to develop more efficient ways to produce crops. Their most recent project is centered around maize, or corn, and is aimed at improving production rate when crossbred with a genetically modified seed. By recruiting help globally, they increase their chances of developing crops to meet their goal of increasing productivity of the world's crops by 20%. And this data's features include location ID, the year, the tester ID, the inbred ID, the tester cluster family ID, the inbred cluster family ID, and the yield. After analyzing the data provided by Syngenta, we arrived at the following conclusions regarding the dataset features. The yield is scaled to be relative to each of the 280 locations. Every yield is a ratio between the expected absolute yield for that particular location and the absolute yield that was recorded. Because we do not have access to the absolute yield, we have no way of comparing results from different locations. The cluster groups were a shared attribute for each seed, tester, and inbred to represent genetic similarity. The time span of the data was short, only spanning 3 years. The test set excluded location and year. Those are two very important features. By using recorded yields provided in the data, the task is to calculate a trend of increased production and identify the critical seed versions. Along with the requirements that were clearly outlined in the project description, the Syngenta team also held online webinars where they would go over some of the important questions and concerns they were given. These webinars were usually accompanied with frequently asked questions document that included very valuable information. We used these documents to verify our findings. For instance, one important analysis that we did at the beginning of this project was trying to understand the relationship of the seeds and their placement in either the tester or the inbred column. By comparing the two seed groups, we came to the conclusion that there were two seeds that were corresponding, both a tester and an inbred. However, the yield we were trying to predict is the yield produced by the combination of seed from each category. Therefore, even if a seed were in both categories, it was to be treated independent from each other. In one of the frequently asked question documents from the webinar, this question was posed, and the answer confirmed our findings that they should be treated independently. With these documents and multiple webinars, we were able to get a better grasp of the challenge presented and save time with our exploration. To analyze the relationship between the features of the data, especially with regards to which features have a strong correlation with the yield, we produced a correlation matrix. The correlation matrix, as seen in Figure 2, only shows the columns and rows with the highest correlations. By asserting that the diagonals of the matrix are a value of 1, we make sure that the correlation matrix was generated correctly, as a feature will always correlate perfectly with itself. Other patterns we noticed are that inbred 2747 correlates highly with tester 3521. This may be because that particular inbred and tester seed pair was tested more often than the other pairs, perhaps because researchers that collected the data observed conflicting results for that particular pair. Furthermore, many other pairs of testers and inbreds are somewhat correlated. Some of the combinations of inbred and tester seeds are more common than others, which may lead to biased data. Finally, it is important to notice that the yield feature does not appear in this correlation matrix, showing that the yield does not correlate well with any other feature. No one seed correlates with high or low yield, meaning that the relationship between the features and yield is nonlinear and complex if it exists at all. Section 2 is metrics. We define the metric functions that we use to evaluate all of our models below. We find all the following metrics necessary, as together they give a comprehensive view of model performance for this task. Our first is root mean squared error, or RMSE, is Syngenta's official metric for our model's performance, and is the square root of the sum of the difference between predicted and true values. A score of 0 indicates that our models fit the data perfectly, and the values range from 0 to infinity. Second is the coefficient of determination, which is a scaled form of root mean squared error. A score of 1 indicates the model fits the data perfectly. A score of 0 means our model performs exactly as well as a mean regressor, which is a model that predicts the mean of the training data for every input. The coefficient of determination effectively gives us a comparison to the baseline within the metric. Values range from -infinity to 1. Mean absolute deviation is simply the average difference between predicted and actual values. This metric may be more interpretable than root mean squared error or coefficient of determination because of its linear relationship with the residual. A set of predictions with a few larger errors would lead to a worse RMSE score than a set of predictions with many small errors, even if both sets of predictions have the same mean absolute deviation. Values range from 0 to infinity. The Pearson correlation coefficient quantifies the relationship between the predicted and actual values using a best fit linear function. This metric does not necessarily correlate with the other metrics because it does not measure absolute difference. Mathematically speaking, a model whose predictions give an extremely bad RMSE are still capable of having an extremely good correlation coefficient. Values range from -1 to 1. Experiment 1 is collaborative filtering. Collaborative filtering is originally an algorithm developed for recommender systems to predict the quality rating users will give to items. We can repurpose the model to predict the yield as it relates to any given pair of features. Collaborative filtering is a good choice for its ability to analyze relationships between discrete variables whose values are orthogonal. Inbred seeds, tester seeds, and locations are all given a specific ID in the data, but no other information about any of the features is provided. By comparing the IDs of two different locations, inbred seeds or tester seeds, we can only know whether or not they are exactly the same. We determined experimentally that collaborative filtering is an asymmetric algorithm. Swapping the user and the item features yields different results. Alternating least squares is non-deterministic by default, but Spark offers an option to start ALS with a seed value. Using the same seed value for one model, using inbred as the user and tester as the item, and another using tester as the user and inbred as the item, we made two models that predicted different results for the same inputs, meaning collaborative filtering is asymmetrical. We are using the PySpark implementation of collaborative filtering, alternating least squares, and the scikit-learn implementation of linear regression. The NumPy and Pandas libraries provide support for these packages. Collaborative filtering requires more advanced processing than most machine learning algorithms. In the training data, only a single row can exist for any given user-item pair. To remedy this, we take the average yield of all rows with the same user-item pair and pass that aggregate as input to collaborative filtering. Collaborative filtering can only analyze the relationship between pairs of features. To compensate for this deficiency, we can use many separate collaborative filtering models of all possible pairs of features, acting as users and items. For complete coverage with collaborative filtering, we need 6 separate models in user-item form. We need inbred tester, tester inbred, location inbred, inbred location, tester location, and location tester, each analyzing one possible user-item pair taken from inbred, tester, and location. After receiving output from all 6 models, those results would be passed through a linear regression model to give us the final prediction. Training. First, we train all 6 models of collaborative filtering. Results from testing the training data with those 6 models are used as training for the linear regression model. None of the hyperparameters changed throughout this experiment. We use the following hyperparameters as values. Experiment 2, Random Forest. One of the most basic regression models is a decision tree. A decision tree finds what feature can be used to split the observations in a way that the resulting groups are as different from each other as possible, and the members of each subgroup are as similar to each other as possible. Using the concept teamwork makes the dream work, a random forest regressor is an ensemble or collection of these decision trees that work together to predict a particular value. It uses the results from each decision tree to factor out individual error and use the majority results to base the predictions off of. By importing scikit-learn, we were able to benefit from their implementation of the random forest regressor package, as well as the mean squared error package to ensure the model was properly set up. We determined the hyperparameters through empirical analysis and then just leveraged the packages mentioned above to produce RMSE and coefficient of determination value. In any implementation of a random forest regressor, the hyperparameters can change the results drastically. To be as accurate as possible, we specify the hyperparameters as follows. The number of estimators or trees in the model was 20. Our decision trees use the mean squared error to determine when to split and make a decision. In order to fully account for the functionality, we set the max depth to none. Experiment 3 is a neural network. In this experiment, we leverage deep neural networks, or DNN, to predict the yield of corn seeds. We also make use of embedding layers, which allow us to transform categorical features into a high-level embedding space. Furthermore, we analyze the embedding space to gain a deeper understanding of the provided data. To process the data, we used Python's Pandas and NumPy libraries. We first read the data into Pandas data frame and converted each categorical feature into a list of integer identifiers in preparation for the embedding layers. Every feature except the year was categorical. We split the provided data into training, which is 90%, and testing, which is 10% sets, and evaluated our models on the testing set. The yield feature was removed from the training set. To train the model, we used the Keras library with a TensorFlow backend. We created an embedding layer for each categorical feature, but used the same embedding layer for both the tester cluster and inbred cluster features. This was because both the inbred cluster and tester cluster feature presented the same set of clusters, and we could interpret them in the same way. Each embedding layer had an output of 2, dimensionality of the output of the embedding, and was subsequently flattened in preparation for the deep neural network. After concatenating all the embeddings and the future year, a vector of length 11 was passed as input into a fully connected deep neural network of 3 layers consisting of 32 nodes, 8 nodes, and 1 node, which outputs the predicted yield. Each layer used the ReLU activation function, and the model was trained with the Atom optimizer for 100 epochs with a batch size of 256 using a loss as defined as the root mean squared error between the predicted and labeled yield. All the hyperparameters used were determined empirically. Analysis of the embedding layers. To better analyze the inner working of a neural network model and to gain deeper understanding of the data, we analyzed the weights of embedding layers after the model is trained. We extracted the weights and performed a t-distributed stochastic neighbor embedding, or TSNE, analysis to reduce the dimensionality of the weights to 2 dimensions so that we can plot the results. Figure 2 displays this visualization. The weights of the embedding layers that process the location features, inbred features, and tester features display a strong order or structure to them, showing that the neural network is effectively using them to make sense of the data. One can see clear clusters developing, especially in inbred and tester features. In the tester embedding layer ways plot, there are clusters in the bottom right, bottom left, and top. Later layers can also separate these clusters and use them to predict yield. From analyzing the produced TSNE visualizations, we can say that the location, inbred, and tester features are being effectively embedded into a high-dimensional ordered space. However, the embedding of the cluster feature does not have clear clusters, making the embeddings display a high degree of entropy. Therefore, we can conclude that the network is able to effectively make useful embedding layers for all the features except cluster features, most likely because there are too few clusters to make useful embedding. Results. We evaluated our model on the testing data using the metrics defined in the metrics section. The results can be seen in Table 1, showing that the neural network performed the best, with collaborative filtering coming in second. Of note is all the models are only slightly better than the baseline and because of the lack of meaningful data that was provided. Discussion. The primary issue with this challenge is the lack of important feature information. The testing data provided to us is schematically inconsistent with the training data, excluding some of the most important features, including location. We would have to adapt our model structures to accommodate this change. For each sample in the test, we could run every possible combination of location and year found in the training set, and then aggregate the predicted yields based on the inbred tester pair that we want to predict the yield for. However, the predicted yields would likely be less accurate because of the lack of location and year information in the test data. Environmental data is completely excluded from the data set as well. Most of the models we designed may have performed more effectively if they had access to more information, such as temperature, precipitation, humidity, wind direction, wind speed, latitude, longitude, timestamp, and absolute yield, not a ratio. More precise genetic information on the seeds would also be helpful because it would allow us to correlate certain genes with good performance in certain environmental conditions. Assuming better information was available, we would be able to use these approaches that deal with more continuous data as opposed to discrete approaches that we took like collaborative filtering. More accurate location and genetic data would make collaborative filtering completely unnecessary and open the door to new possibilities with many other models that work more effectively with continuous data, such as boosting. Conclusion. By exploring a myriad of possible models to predict the yield of corn, we determined that the neural network model with the embedding layers and the collaborative filtering model perform the best in this task. The two models are similar in their mean absolute deviation and root mean squared error, but differ in their coefficient of determination and Pearson correlation coefficient. It would be possible to explore the data even further if more features were present in the data. We could have made more flexible models with continuous data, which is mathematically easier to process. Future work includes research on more extensive and descriptive data that Syngenta provides to us if it provides it in the future. And that's it. Thank you.